Thank you so much. Good morning. Hi, I'm Jens. This is my first Tableau. But I'm very happy to be here, and it's also the first basically contribution to Tableau systems that we have worked on. So this is joint work with Torben Braüner, and we are at Roskilde University. And so as the title says, a Tableau system for first-order logic with standard names, and that's a logic that is called L. It was first proposed by Levesque and Lakemeyer. And basically, so it's a first-order logic with functions and with equality, but it's based on standard names. And standard names are a countable infinite sets of names, which we denote by number 2, number 1, number 2, number 3, and so on. And what is non-standard here with this logic is that these standard names, they serve a dual purpose. They are both a fixed universe of discourse, but they are also part of the language, right? So we can use them inside of formulas in the same way that we would use constant symbols. And so this logic has a relatively long history already, goes back to the early 80s. It was basically developed in the context of first-order logics of belief and a so-called only knowing, also by Levesque and Lakemeyer. And since then it has been kind of applied, or this idea of using standard names has been applied and extended to many different types of modal logics. For example, for non-monotonic reasoning, for action and change, more recently about logics for agent programs and temporal specifications. So there we have some work on verification and program synthesis. And so they have basically in common that L is kind of the non-modal subset, the non-modal fragment of these logics. So there has been quite a lot of work on this, but somewhat surprisingly, so far there's not been an implementation of a sound and complete reasoner for this base logic. And what comes closest perhaps is, of course, Levesque and Lakemeyer. They originally proposed this Hilbert-style axiom system, but that is, of course, not suitable for actual reasoning, but it's more meant as a kind of tool or a means of studying the theoretical properties of the logic. There's another line of work where Schwering worked on an implementation of an incomplete reasoner. And there the focus was, however, more on tractability, and basically incompleteness is taken into account for that. And finally, more recently, Lakemeyer and Levesque also presented this reasoning mechanism for L that is based on resolution and subsumption, but it could be argued this is not an analytic method, right? And so with this paper, we basically presenting, as far as we know, the first sound and complete Tableau system for L, and this would also be the first analytic proof system. Yeah? So there's no sequent calculus or anything that has been studied up until now. All right, so a little bit about the formal details. As mentioned, in terms of syntax, it is pretty much like first-order logic with functions and with equality. And standard names can just used where we would use constant symbols, right? For the semantics, for basically historical reasons, right? So because in the literature, right, they developed this as kind of a base logic for modal logics of belief. And therefore, a semantic model is called a world here. But so this is really just, think of this as an interpretation. And such a world is a mapping from the so-called primitive atoms into truth values. A primitive atom is just a predicate symbol applied to only standard names. And in a similar fashion, a world maps the so-called primitive terms into values, which are other standard names, and a primitive term is just a function symbol applied to standard names. Yeah, and once we have that, so we can evaluate ground terms just by mapping every standard name into itself, and nested terms can be evaluated recursively using the mapping for primitive terms. As for formulas and sentences, so I'm not going to go through the whole list here, but basically I highlighted in colors what is non-standard about this logic. So first of all, we can see that for equality is basically interpreted as identity over co-referring standard names, right? So if we have an equality over terms, then we look at what standard name does our world map each term to, and if they happen to be the same standard name, then they are considered equal. The second non-standard thing is that quantification is interpreted substitutionally. So if we have a formula that exists x phi, then that is true in a world just in case that we have some standard name n that we can substitute for x, and then that resulting sentence is satisfied by the world, right? So Levesque and Lakemeyer also presented this axiom system as mentioned, and again I highlighted more or less in the same colors what is non-standard about this. So in green you can see that the axiom 6 formalizes again equality as identity over standard names, right? So that every standard name is of course equal to itself and distinct standard names are unequal. The orange part is also non-standard. So this is a universal generalization inference rule where basically to infer a formula for all x alpha, we need finitely many instances, right? So we look at alpha, we substitute the variable x by a finite number of standard names. And if we have a proof for those, then we can infer for all x alpha. And the standard names that we look at here, they have to range, of course, over all the names that occur in the formula alpha, plus a single one that does not occur. And here the idea is, okay, the single standard name that does not occur is kind of a representative for every other standard name that does not occur, because the proof will have exactly the same structure, and the only thing that we need is to basically substitute one standard name for the other. Yeah, so this is basically an idea that we will follow throughout the talk here. Yeah, just to give you one example of a proof, I'm not going through the whole thing, but if you look at the last line, number 8, this is the formula that we want to prove. This is the substitutivity property for functions, right? So when x and y are equal, then f and x and f of y are also equal to itself. And so this, if we basically read this backwards, we can see that we infer formula 8 from formula 7 by means of the universal generalization rule. And because formula 8 doesn't contain any standard name, we really need only one single instance for an unmentioned standard name, for example, number 1. And that is precisely the formula at line 7, right? And then 7 in turn is also inferred by means of this universal generalization rule from the formula at lines 4 and 6. And because the formula 7 has a standard name number 1, we need 2 instances. We need the instance with number 1, which is the line 4. And we need an instance with a non-mentioned standard name, for example, number 2, which is exactly the formula at line 6, right? So yeah, and so I'm showing you also this now because this is basically the inspiration, or was the inspiration for us to develop the Tableau system for L, which we have here. And so this is basically the result. It took a little bit of time to figure it out and to do the fine-tuning. But this is what we ultimately came up with. And once again, the non-standard things are what is depicted in orange and in green. And so perhaps the most interesting part is the rule for the existential quantifier. And it follows exactly the same idea, right? So we look at basically all the standard names that occur in not only in the formula exists x alpha, but also, of course, all formulas on the branch that we are currently on. And then we take those standard names plus an extra standard name that does not occur, and then for each one of those instances, we create a new branch, right? And so basically the existential quantifier is mapped to a branching over finitely many instances. To handle functions and terms, we have these t-cut and t-sub rules. So the T sub is basically just substituting a ground term or a primitive term by a standard name as its value. And the T-cut rule follows the similar idea as the existential quantifier, right? We make basically a finite case distinction, look at all the names on the branch, take one extra, and the value in the sense of a standard name for this term must be then one of those finitely many instances. Yeah. Finally, we have a new closure rule, which is the one here in green, the equality. So if we have an equality over two distinct standard names n and m, then we can close the branch because that's unsatisfiable. So yeah, let me show you an example. So here's the same formula that we saw in the proof before, just negated, right? So that's negation of the substitutivity property for functions, of course, because we want to show unsatisfiability here. And so, yeah, we start out with an existentially quantified formula, not mentioning any standard name. So we need a single instance by standard name 1. This is what we get in the first step. Now we have another existentially quantified formula with a standard name number 1. So we create 2 branches in the next step, right, with instances or y instantiated by number 1 and number 2 on the right-hand side. In the left branch, we can apply the normal rules. So it's a negation of an implication. So we would apply a rule for conjunction, and we take the negation of the right-hand side conjunct. And then we can close the branch with the usual inequality rule, because we have an inequality over the term being equal to itself. On the right branch, yeah, we take the left-hand side conjunct, also with the conjunction rule. And that is again an equality over distinct standard names, which we then can close with our new closure rule for equality. Yeah, so I think it looks pretty nice. So, yeah, as mentioned, it took us quite some time to come up with this, but we're quite happy with that. One more example to show you also how we deal with functions and terms. Yeah, so here we have a set of 3 formulas with constant symbols, right? So standard constants that may or may not be equal. And of course, this is a set of formulas that is not satisfiable. But so here we would apply our T-cut rule first to the constant a. Yeah, basically assign it one possible value, and again, there's no standard name in the original set of formulas, so we just take any unmentioned name. Here we take number 1. And then what we do is basically we substitute this value for a in the formula in the first line, and we do the same for the formula at the second line. Now we apply the T-cut rule again for the other constant b, and now of course we have to create 2 branches because there is a name, and then we instantiate by that name, or we assign that name as a value, and then we assign another name as a value that does not occur yet. And on the left branch, we then again apply the substitution rule to substitute this value of b into the formula at the third line. And then this branch can be closed due to there being 2 complementary literals, right? The right branch, yeah, we substitute the value of b in the formula at line 5, which gives us again this inequality, this equality over distinct standard names, and that, as before, we can close with the new closure rule. Yes, and so basically, it could be argued that this is kind of a rather kind of analytic way of handling functions and terms, because we're basically systematically substituting subterms by their values, namely names, right? And should we have nested terms, then we would basically systematically decompose them into the subterms and then assign values to the subterms. All right, and so yeah, in the paper, of course, we have theorems on soundness and completeness. Soundness, I think, is relatively straightforward, that we use an induction over the structure of the formulas. to show that any of the expansion rules preserve satisfiability. The completeness proof was not as straightforward, but we basically follow the chapter by Letts in the Tableau handbook in the overall structure, but we had to add a little bit more of a detail that we had to flesh out. The general structure is that we build a saturated systematic Tableau. Basically, we specify a certain order in which we select nodes and apply the rules. And here we have a certain specific lexicographic order that we use for that. And then we basically build like this infinite limit Tableau. And if there is a branch on this Tableau that remains open, basically in the limit, then we show that this is a satisfiable branch using a variant of Hintikers sets, right? And we have a variant of Hintikers lemma for that. Yeah, so basically in structure, relatively standard, but of course we had to adapt to had to adapt this to our new notions of satisfiability. Yeah, and so that's pretty much it what I wanted to show. So in the paper we have a few more discussion points, maybe that I want to highlight here as well. There is first of all, one kind of fundamental difference perhaps is that our Tableau system only works on finite inputs. Yeah, so you cannot use this for infinite sets. The reason being that L is not a compact logic. Yeah, so here's an example of a set where yeah, the set is an infinite set that is obviously unsatisfiable, right? So there is an xp of x, and then I enumerate not p of 1, not p of 2, not p of 3 for all standard names. And so if you take any finite subsets or even any subset of that, it becomes satisfiable because you can just make p true for the name that is then not mentioned. Yeah, and so here it might be worthwhile, of course, that's beyond the scope of what we did in the paper, but it might be interesting to look at extended notions of compactness that have been studied for infinitary logics. In particular, omega logic is, I suppose, very close to L. Then there was also kind of a philosophical argument, a philosophical discussion around substitutional quantification. In the 70s, I suppose, there were papers by Wallace and Thorpe, and there was kind of this fear or worry that this would lead to a lack of ontological commitment, right? So that basically, if you accept substitutional quantification, really that means ultimately it may lead to a situation where nothing exists. Yeah, however, there was this paper by Kripke, so the paper is titled, "Is there a problem about substitutional quantification?" And in the conclusion, he says there never was a problem about substitutional quantification, so that was quite reassuring to read. But specifically, he kind of argues that the substitutional quantification that we use here and the classical referential quantification, they are more or less the same under these two conditions, namely that the denotation function for terms is total. Yeah, so every term is mapped to a value, to something that exists. And all the formulas are transparent, which means that it may not happen that by substituting something by something else, the truth value of the formula changes, right? And both conditions obviously are true for L. And so, yeah, we just want to point out basically that the standard names are kind of like the rigid designators that Kripke talks about in his famous book. Yeah, but so really the whole motivation behind this work was towards an implementation of a reasoner. And we believe that this system lends itself very well to this kind of reasoner, but of course the next step would be to kind of do some quantitative evaluation and implementation, of course, first to substantiate this claim. And therefore we are at the moment developing a prototype in Prolog, similar in spirit to LeanTab and other similar systems for classical predicate logic. And also in the long run, we're then interested in guaranteeing termination so that we get for basically for decidable fragments, a termination guarantee. Yes, so that's it from my side. Thank you for your attention, and I'm happy to take